Welcome to my channel. I am Dr. KP Naidu. In this lecture, I am going to discuss about the linear SVM classification. Clear? So, as we already discussed about what is meant by linear SVM and what is meant by nonlinear SVM. So, in this lecture, we are trying to understanding a piece of code how to implementing the linear SVM classifier. The linear SVM classifier is implemented using two classes in scikit-learn library by using SVC class. Another one is the linear SVC class. Okay, so let us try to understand how to implementing the linear SVM using the linear SVC class. So here I am using the iris dataset. So by default dataset I am loading. That's why first I am importing the dataset. From the dataset I am loading the iris dataset. Okay. So the capital X contains all the independent features. The Y contains the target features. Actually the independent features are sepal length, petal length, sepal length, sepal width, petal length and petal width. But in this scenario, okay, to the X, I am taking all the records of petal length and petal width only. That means iris of data. That means all from the independent variables. We have to take all the records from column 2 and column 3. The column 2 contains petal length. The column 3 contains petal width. Okay. So that means to the X we are getting all the records of petal length and petal width. To the Y, okay, we are maintaining the target variable. Target variable. The target variable in iris dataset contains three types of classes. Okay, so in those three types of classes, the value 2 contains to the class called as Virginica. Okay, so to the remaining classes, that means we're having class 0, 1, 2. Okay, so equal to 2 means that is class belongs to which one? Iris Virginica. So what we have to do here is, okay, if the iris of target equal to 2, okay, that is belongs to Virginica, it returns a true value. It returns a which one? True value. If it is true, then we have to convert the true value into the floating point. The floating point by using the function called as type of np.float of 64. That means the true value is converted to float value, that is called as 1.0. That means actually this function returns true if target equal to 0, 2. Okay, it returns true. But actually into the target variable we are maintaining either 0.0 or 1.0. If the y equal to if the y equal to 1.0 means that record belongs to a Virginica, or else that instance belongs to which one? Another class. Okay, that may be Setosa or some another class. So now here I am creating one pipeline. Okay, so in that pipeline I am using the standard scalar function. The main purpose of the standard scalar function is it can standardizing the data. So here to build a model, here I am using the linear SVC function. So in this linear SVC function, okay, the main purpose of the linear SVC function means it can use to build a model for linear SVM classifier. So in this I am using one parameter called as c equal to 1. It is regularization parameter. If the value of c equal to low, okay, it gives the maximum margin. If the value of c equal to more, it may gives the less margin. Okay, this is also we discussed in the previous videos. And last is the one of the optimization, one of the error parameter. Okay, so this error parameter can be used to optimizing the SVC. Okay, so likewise we have to create in the pipeline. Once if we create in the pipeline, okay, so to create a model, okay, so we are using the SVM CLF dot fit. We are passing the x comma y. Okay, so this is the simple linear SVM classification. Okay, build a model on which one iris dataset. So as already discussed about, we may also implementing linear SVM classification either by using the linear SVC function or linear SVC class, and also with the help of the SVC function also. Here writing linear SVC function, we may also replace this linear SVC function with the function called as SVC. From the SVC function also we may implementing the linear SVM classification, but here we are passing the kernel equal to linear. Okay, as we already discussed, the C is a regulation parameter. Okay, it may be either 1 to some another value. And another approach to implementing the linear SVM classification is we may also implementing by using SGDC. That means stochastic gradient descent classifier. We may also using this function to implementing the linear SVM classifier. Okay, so that is three different ways to implementing the linear SVM classification. Hope everyone understood how to implementing the linear SVM. Okay. Now coming back to the non-linear SVM. Non-linear SVM. Okay. So as we know that the non-linear SVM means we are not separate the data. Okay. So to handle the non-separable data, to handle that non-separable data, we are using the kernel tricks. We are using which one? Kernel tricks. What the kernel trick can do is, what the kernel trick can do is, it can map the input data, what the actual data, what the non-separable data we are having. That non-separable data or some input data is transformed or is converted into high dimensional space. When we are mapping the input data into some high dimensional place, then there is chance to converting that non-separable data into separable data. Clear? So to converting that non-separable data into some high dimensional place, high dimensional space, we are using the different kernel tricks. Okay, so this is general equation to define the kernel trick. We are having different types of kernel tricks. So to define any kernel trick, we are using the function. We are defining a function like this: k of xi comma xj equal to phi of xi into dot product with phi of xj. Here phi of dot means the mapping function. This may be one function. This may be some another function. We are providing some dot product between these two functions. Then we are getting some another value. Okay, so let us see some examples of nonlinear SVM. Let's see this one. We are having some blue class points and green class points. Okay, but it's not possible to separating these 2 points by using the linear SVM. Then what I am doing here is, here only having x1. This was converted into both x1 and x2. That means I can increasing the number of features. Here we are having one single feature. I was increased to 2 features, x1 comma x2. If I am increasing the single dimensional input data into two-dimensional space, now we can see that this is the, let's say, the margin. This contains the green class points. This contains the blue class points. That means when we are mapping the input data into high dimensional space, then there may be a chance to separable the separates the classes or separate the data points. Okay, that is one example. Okay, so if you want implementing the nonlinear SVM, that is also possible. The nonlinear SVM is also implemented by using the what is called as linear SVC function. Linear SVC function, but it is not directly implemented that nonlinear SVM using the linear SVC function. Okay, so here what we have to do is we have to creating the one pipeline. So in that pipeline we are passing one function called as polynomial features. If I am taking the degree equal to 3, that means here I am using the polynomial kernel Later we will see how it can works. That polynomial kernel with degree equal to 3 as standard scalar to standardize the data. Okay, and then only we are using the linear SVC with some regulation parameter value and the some loss function. Here I am using the hinge loss. Okay, by this code also we are implementing the non-linear SVM classification using the function linear SVC. Okay, not directly we are using the non-linear SVM classifier. Here I am using the linear SVC function, but to this we are adding one kernel trick that is called as the polynomial kernel with the function polynomial features. Okay, so this is another some example of which one non-linear SVM classification. Okay, so if you are using the linear SVM classifier, here I am taking the degree equal to 3. Okay, so if I am taking the degree equal to 3, so the data is separated like this. That is separated like this. So below this curve we are having on green class points. Above this curve we are having all the blue class points. But let us see in the blue class points we are having one green class points also. If you are trying to removing or if you want to classifying that point also. Okay, so by increasing the degree we may also classify or we may also converting this point to this area also, maybe by increasing the degree or by increasing the value of c. Okay, later we will see. Okay, so this is some more examples of nonlinear SVM. This is some x only x feature data. It is non-separable data. By increasing the x with x comma x square, now there is chance to separate the data. Here also one more non-separable data. Okay, so what I am doing is the two-dimensional space I can increasing as some x square and y square. That is, this one is x, this one is y. By squaring the x and y, then again we are trying to plot, then it can separate the data. That means we are converting one dimension to another dimensions, then there may be chance to converting the non-linear data into linear data. Okay, so here I am taking as this is a non-linear data, two-dimensional space that was converted into some three-dimensional space, then there may be chance to separate the points like this. So what we are understanding till now is, so to converting the non-linear data into linear data, we simply uh, mapping the input data into some high dimensional space, then there may be chance to converting the linear data into so non-linear data into linear data. Okay, so to converting that non-linear data into linear data, we are using the different kernels. That may be linear kernel, polynomial kernel, RBF kernel, sigmoid kernel, or custom kernel. Okay, so custom kernel means user can create its own kernel. From that kernel also we may separate in the non-linear data into which one linear data. Okay, but here we are mainly focusing on about these four functions. Okay, first one is called as a linear kernel. It's called as one linear kernel. So as you know that the hyperplane function is w transpose x. Okay, the plus what's called as b. This may be a one what's called as hyperplane or some straight line equation. Okay, the same one here I am applying here. Okay, so that means the w transpose may belongs to xa transpose, the x may belongs to a some xj. This is some linear kernel equation. So this linear kernel is used when the data is linearly separable. Okay, the example is hyperplane in the original feature space. Original feature space. Okay, so when the data is linearly separable, for example, if in the above we are having all the positive class points, in below we are having some negative class points, then we are using the kernel is called as the linear kernel. Okay, so by default, if you are using the linear SVC, by default it was using the linear kernel. Okay, if you are using the SVC function, we have to mention kernel equal to linear, then it will automatically apply. And polynomial kernel, simply we know that what are the equation, y equal to W transpose X plus what's called as some bias beta. If you're increasing the degree, okay, to this equation, then that kernel becomes a which kernel? Polynomial kernel. It was simple. W xi transpose xj plus c. We are increasing the which one? Some degree. Okay. So here c is the some coefficient, d is the some degree. Okay. So when we represent polynomial kernel, if we are visualizing the data having some polynomial relationships, then we are applying the polynomial kernel. Okay, so now how much degree we are choosing? Okay, at low polynomial degree, this method cannot deal with very complex data set. With high polynomial degree, if you're choosing the more polynomial degree value, okay, the model becomes a slow. That means choosing the polynomial degree is also a challenging task. Okay, now here I am implementing the SVC, okay, classifier. Okay, so using the kernel trick, okay, that is kernel equal to poly. Here I am using degree equal to 3, coefficient and some regulation parameters equal to 5. The standard scalar function is to standardize the data. I am creating one pipeline. Okay, so to this pipeline I am passing the uh, polynomial kernel SVM CLF, okay, dot fit function. If I am using the degree equal to 3, let's see here, degree equal to 3, this is the curve we are getting. Okay, so but in this curve, in this place, we are having some green class point also. If I am taking degree equal to 3 and some c equal to 5, okay, some r equal to 1. Let's see if I increase in the degree. If increasing the degree, let's see all the points below this curve having the green class. Okay, and remaining points are having the above this curve. That means by increasing the degree, there may be more chance to easily there is more chance to classifying the points into uh, its corresponding regions. Either it may be green class, either it may be which one? Blue class. Okay. So another kernel to solving the nonlinear data in SVM is called the radial basis function kernel. That is called as RBF kernel. It is also called as Gaussian kernel. Okay. Its function is exponent of minus gamma modulus xi minus xj whole square. Okay. So what the gamma can do? Gamma controls the influence of the single data points. Small gamma data points have broad influence, large gamma narrow influence. That means if you are using the kernel equal to RBF in SVC function, here the gamma works as a regulation parameter. A small gamma value gives the broad hyperplane, if the larger gamma value gives the narrow hyperplane. Okay, narrow hyperplane. So if you're using the larger value of gamma, there may be chance to getting the overfit. Okay, so this is another example as we already seen that. Okay, so how we are implementing that radial bias, radial basis, okay, function are also called as Gaussian kernel. Okay, so here what I can do is we are using this measure similarity of each point, okay, to these two landmarks. Okay, so induce two landmarks. Okay, so that means we have to uh, join or locate all the similar points into one landmark and another similar points into some another landmark. Then we have to separate. Okay, then from this we are getting the, in one region we are getting the blue class points, in another region we are getting the which one? Green class points. Clear? So now from the SVC RBF, what how it can be helpful means polynomial features additions becomes slow. That means if you are increasing degree of the polynomial, okay, the model becomes slow. Then that the problem may be solved with the RBF. Okay, here also similarity function becomes slow with higher number of the training data set. If you're having the more number of records in the training data. So find out the similarity measures. It may take the more time. Okay, so anyhow, choosing the best kernel for solving the nonlinear data is also a challenging task. Okay, so to implementing that nonlinear SVM using the kernel RBF, simply we are passing kernel equal to RBF. Here gamma works as a regulation parameter. Okay, if the model is, if the gamma acts like a regulation parameter, regulation hyperparameter. If your model is overfitting, you reduce it. If it is underfitting, you should try to increase it. Gamma val is more, there may be chance of which one? Overfitting. If gamma value is less, there may be chance to getting some underfitting also. Okay, that is about RBF. Here we can see that gamma equal 0.1, C equal 0.001. So it is separable some hyperplane, but in this region we are having some both blue class and green class points. If gamma equals 0.1, C equals some 1000, in that time also in the blue class region also we are having some green class points. If gamma equal to 5, C equal 0.001, here also we are getting some green class point in some blue class region. If gamma equal to 5, C equal to 1000, let us see we're getting one car. Okay, that car having linearly separable both blue class and what's called as the green class. Maybe this may be best values to separate the both green class and blue class points. Clear? So that is about another type of kernel trick is called as the sigmoid kernel. This sigmoid kernel is mainly applied for which one? Neural networks that will be discussed in the next coming videos. Okay, the function for this one is k of xa, xa equal to tan h, simple. Like, okay, here just we have to add some scaling factor. For the scaling factor we are applying some tan h function, then we are getting some values. Okay, that is what's called as the sigmoid kernel. Okay, so it mimics the neural networks, that is called as tan h activation function we are using. Okay, so here the main question is which kernel to use when. That is the main confusion while building the model for nonlinear data. Okay, so try with linear kernel first. Okay, so if the train set is very large or too many features, try with some linear SVC. If the training set is not too large, try with better to Gaussian RBF kernel. Okay, or if you are using some what is called as some hyperparameter uh, tuning techniques, that is called the grids HCV, random HCV. From that also we are using different combinations of kernels, a linear, polynomial, maybe some RBF or some sigmoid kernels. So from the grids HCV we have to find which kernel is better with the help of the cross validation also. Okay, from that scenario, by using that scenario also we are finding the what is the best kernel. Okay, so these are some of the differences between different types of kernels. Okay, the linear kernel use case is used for linear separable data. The polynomial kernel for polynomial relationships of data. The RBF is generally non-linear relationships of data. The sigmoid is used neural networks like behavior. The strengths are fast and interpretable. The polynomial is flexible. The RBF strength is handle complex data well. The sigmoid kernel strength is simple and intuitive. Okay, the weakness of linear is poor with nonlinear data. The polynomial kernel weakness is computationally expensive. The weakness of RBF is risk of overfitting. The sigmoid kernel weakness is sensitive to parameters. That is all about the different types of kernels, what is meant by the kernels, how to solving or how to build SVM model for nonlinear data. Okay.